You tell your AI assistant to grab a new coding tool from the web. It complies, but instantly your machine is hijacked. The AI assistant fabricated the path to the malware itself, requiring no external phishing link or social engineering. Researchers call this exploit HalluSquatting. It weaponizes a core flaw in large language models, their habit of confidently guessing facts when they don't actually have the answer. By tricking coding assistants into acting on those wrong guesses, this exploit breaks the trust model of modern software development, turning the AI into an active insider threat. Modern developers frequently give AI agents like GitHub Copilot or Cursor direct access to their terminals. These agents pull code from repositories and run scripts to speed up daily workflows. This diagram illustrates older AI exploits, like prompt injections. They required an attacker to push malicious instructions to one specific target at a time, say by sneaking bad code into a single calendar invite. The process is slow and difficult to scale. Hackers looking to assemble massive networks of compromised machines don't want to hunt individual victims. They need thousands of computers to infect themselves all at once. To achieve that, they need a pull-based method. The attacker has to lay a trap on the open internet and wait for AI agents to fetch the malware on their own. The foundation of this trap relies on a blind spot shared by all major language models. When an LLM doesn't know the precise web address of a requested resource, it almost never says, "I don't know." This chart maps how often AI models hallucinate resource locations. While they accurately locate older, pre-2019 repositories, if you ask an agent to clone a brand new tool from 2025, the AI fabricates the location nearly 100% of the time. In a traditional typo squatting attack, a hacker relies on a human making a spelling mistake. Here, the AI is completely inventing a web location that has never existed. This logic flowchart shows how models process requests. When prompted to install a new tool, models consistently fall into a self-referential loop. Instead of finding the true author, the AI outputs a duplicated structure, using the tool's name as both owner and repository. Because all major LLMs follow this same duplication pattern, an attacker can pinpoint the exact identifier a model will invent for any new tool. To execute the trap, an attacker monitors registries for a new tool. Using those known hallucination patterns, they predict exactly which fake location the AI will invent to look for it. The attacker then registers that fabricated location on a legitimate registry like GitHub and uploads a decoy package that mimics the trending tool. Hidden inside that decoy, often tucked away in a simple README file, is a script designed to install a reverse shell, giving the hacker backdoor access to the machine. The trap is now set. A developer wants to try the new trending software, asks their AI assistant to install it, and hits enter. Confidently bypassing the authentic software, the AI hallucinates the expected fake path. It navigates directly to the attacker's squatted repository and downloads the decoy package. Because coding assistants operate with high-level command line access to streamline the developer's work, the AI automatically executes the malicious script on the host machine. The AI assistant uses its administrative permissions to install the malicious script directly, bypassing external security protocols entirely. Because the attacker targets tools that are currently trending across the tech industry, they don't have to pursue individual targets. Thousands of developers ask their AI agents for the same tool, and thousands of agents independently make the exact same hallucination. This network map shows what happens next. What starts as a single infected node rapidly branches out, simultaneously compromising large numbers of independent developer machines and linking them together under a single attacker's control. Once a hacker controls that much combined computing power, they can deploy it for widespread, coordinated operations. This includes large-scale cryptocurrency mining, distributed denial-of-service attacks, or rolling out ransomware across multiple corporate networks at once. By harnessing the predictability of text generation, HalluSquatting turns an annoying coding error into a highly scalable mechanism for mass infrastructure infection. Software marketers frequently pitch AI coding assistants as frictionless tools capable of fully automating tedious workflows. Yet this entire system rests on an unpatched vulnerability, deeply embedded in how major foundational models process information. Current security measures often focus on filtering malicious output or restricting specific commands. These tools can limit the fallout, but they do not stop the AI from navigating to a fabricated repository in the first place, leaving the underlying tendency to hallucinate unaddressed. As we grant AI agents greater autonomy and terminal access to execute code, the risk of automated network compromise scales right alongside it. We can no longer treat AI as an infallible coworker. Securing our networks requires acknowledging that these models are untrusted systems, and that any action they take demands mandatory human verification before a single line of code is run.